This is Premise Podcast number 54, and today we're talking about the biggest error that aerodynamicists make. And the reason why this is the biggest error is pretty much because most aerodynamicists make it, and that is not measuring the density of the air that they're using. So, to give you a scenario, let's say you're doing some experiments, or you're doing CFD or whatever, but you need to do some sort of experimental campaign. So what do? You go into your wind tunnel and you have your setup and everything, and you say, okay, I want to run this wind speed at 15 meters per second, or whatever you want to measure it, run it at. So you go, okay, well, to figure out what the velocity of the wind tunnel is, I then need to calculate what the dynamic pressure should be for 15 meters per second, and then measure it in the wind tunnel and then line it up. So what you do is you go, okay, the dynamic pressure equals half times the density times by the velocity squared. So I know the velocity, I want it to be 15 meters per second. And then you say, okay, well, the density I'm going to assume is 1.2 kilograms per meter cubed, or 1.225 kilograms per meter cubed, whichever of the two standards that you typically use. From there, you then calculate the dynamic pressure by going half times the density, 1.2 kilograms per meter cubed, times the velocity, 15 meters per second squared. So you then get the dynamic pressure of 135 pascals. And you go, okay, so I'm going to go into the wind tunnel, and I want to get my wind speed to get to 135 pascals in the dynamic pressure when I put my pitot-static tube in there. So I want the difference between the static part and the pitot part to 135. When I get there, I know the velocity is then 15 meters per second. Except it's not. The reason why it's not is not because the velocity you want is not correct. You know you want the velocity of 15 meters per second or whatever velocity you want. It's because of the density. And so let me give you two conditions to highlight how these errors come about. So for condition one, let's say it's 15 degrees inside your room, your wind tunnel. And let's say it's 100,000 pascals and it's a relative humidity of 75%. So this is a typical, either a morning or a typical autumn, or I mean fall for my American amigos, day. So 15 degrees inside Celsius, which is about, 55, 60 degrees Fahrenheit, is a pretty normal operating temperature inside a wind tunnel on lots of days and in the morning. So if you were to calculate the density based on the temperature, barometric pressure, and humidity, which is very easy to do anyway, you get the density is 1.203 kilograms per meter cubed. That's pretty close to 1.2, which you assumed. Very nice. So if you were to measure 135 pascals in your wind tunnel due to the dynamic pressure, the velocity that you get would be pretty close to what you want. It would be 14.98 meters per second. There is obviously a slight error in there, but it's pretty close. That's for condition one. For condition one, I should mention, is ideal. I picked that because it's ideal. Condition two is not ideal. Let's say inside your wind tunnel is now 25 degrees Celsius. And that's very common. That's like about 80 degrees Fahrenheit. So 25 degrees Celsius is a typical operating temperature in a wind tunnel again, and that could be whether that's a spring day or later in the day or mid-morning or during midday in a summer day. And let's say the barometric pressure is 101.3 kilopascals, so the typical quintessential barometric pressure that we all use as an assumption, by the way, but it changes every day. It can change between 98,000 and 103,000 is a very typical operating range. And let's say that the humidity is 30% or 32.5%, let's say. If you calculate the density from there, again, these are all very typical conditions. The density is actually 1.179 kilograms per meter cubed, not 1.2. There's about a 2% error in your density now. So if you were to go into your wind tunnel and you measure the dynamic pressure with a pitot-static tube or whatever other instrument you like to use, pick your instrument of choice, and then you calculate the velocity from that with the actual density that you have, which is 1.179. The real velocity is 15.133 meters per second, 1% different. So that's a massive problem because you might think, okay, that's 1% error in the velocity, but if you think about the change in the flow physics, it has a big effect. For example, the Reynolds number will be different by about 3 or 4%. And so, for example, if you're testing, let's say, a wing at a Reynolds number of 100,000 or so, that's right in the prime range for a laminar separation bubble to form. And if you haven't learned about LSBs, I've done lots of podcasts on them. You can find them in our history, and you'll know that after you watch them that the LSB is very, very sensitive to the Reynolds number. Even a 2% error or 1% error in the Reynolds number will dramatically change where the LSB starts and ends. Or alternatively, I have a picture here which is of a couple cylinders. We'll look at this later actually. This is some simulations that I've done to show you the difference in the flow physics that occurs due to errors in the density. But just now, I can briefly mention if you have a cylinder and you have an error in the Reynolds number by about 3 or 4%, the Stroll number will be significantly different, especially in certain Reynolds numbers ranges. So for example, below about 10,000 Reynolds number and above about 150,000 Reynolds number, the Stroll numbers really change dramatically with just a small change in Reynolds number. Then you have errors in the viscosity and everything else. And that's what happens with the errors in the density. So to show you what these errors are, I'm going to show you these videos. So this first video, there are two cylinders. There is the one on the bottom, that's for condition 1. That is when you have a temperature of 15 degrees Celsius. The barometric pressure is 100,000, which is, or 100 kilopascals, which is very normal. And the relative humidity is 75%, again, very normal. So this is very close to ideal conditions, 1.203 kilograms per meter cubed. That's the bottom cylinder. The top cylinder is for condition 2, where we had 25 degrees Celsius, 101.3 kilopascals, and 32.5% relative humidity. So the density is 1.179 kilograms per meter cubed. So I'm going to run this, and I'm going to pause it. And at the start, actually, you can see that I haven't played it yet, but at the start, you can see the vortices are all lined up. So a cylinder is going to have a quintessential vortex of von Karman Street. And the reason why I chose von Karman Street is because everyone loves a good von Karman Street. It's the quintessential aerodynamic phenomenon. So at the start, these vortices have been aligned. I've made them in sync. But as we play, you can see it doesn't take too long before they start to become out of sync. Now, even now, they're out of sync by like 20 or 30 degrees. And that's because the velocities are different and the Reynolds numbers are different. So the vortex shedding is different. The Stroll numbers are different. So let me explain how they're different. So if you didn't measure the density and you just put these cylinders into your wind tunnel on any given day and you ran it and you assumed that you had a 15 minutes per second flow, even though the top one is 15.133 and the bottom one is 14.98, if you were to calculate the Stroll number of the bottom one, first of all, you get the frequency shedding is 2.18 hertz. The top is 2.205 hertz. So again, you have about 1% or so difference there. The Stroll number on the bottom one, if you were to use the velocity that you want, is 0.167 instead of the top one is 0.169. So again, you get a percent or so error right there. Actually, I should mention these are actually at lower velocities. I did them at lower velocities so we could see them. These are actually at velocities of 0.13 meters per second, but the same relative errors occur. It's just that I've scaled it down so we can see it in real time. So the Reynolds numbers become about 90. So that's a big problem. Now, that was the first simulation that I did. I did another simulation which is on airfoils. And the reason why I chose airfoils is because airfoils, again, are a quintessential aerodynamic phenomenon. Let me make this screen a little bit lower so we can get a bit more of the color bar. The color bars range from the exact same thing. It goes from minus 150 to 150 pascals gauge. So again, the bottom one, these are two simulations that I've done just to represent what would happen in a wind tunnel. So in this case, the velocity was 15 meters per second we wanted. So assuming you go into the wind tunnel in condition 1, which is the bottom condition, the bottom flow, we have the velocity is actually 14.98 meters per second. The top airfoil was for condition 2, where we have the velocity is 15.133 meters per second. That error is there because of the change in the atmospheric conditions, the temperature, the barometric pressure, and the humidity, the relative humidity. Now, what would happen when you do your experiment? Say you want to figure out what the lift and drag are of these two wings. So you would do your experiments, and then you want to normalize these or non-dimensionalize these two forces that you measure, which will be different, by the way, because the forces on these will be different because the velocity is higher for the top one than the bottom one. But you get these forces, and you're under the assumption that both of these runs were at 15 meters per second. Then you use that 15 meters per second in the lift and drag coefficient equation. So you know how lift equals half times the density times velocity squared times the area times the lift coefficient. And then the drag coefficient, the drag, sorry, is the same, but with the drag coefficient instead of the lift coefficient. So you just rearrange the equations to get the lift coefficients and drag coefficients. So for the bottom situation, if you were to do that, this is a wing at 17-degree angle of attack, NACA 0012, and you would get a lift coefficient of 1.131. You get a drag coefficient of 0.091. Now again, these are pretty close to what they should be because the velocity is very close to 15 meters per second. It's 14.9 for the bottom one. For the top condition though, again, we don't know that these velocities are different because we haven't measured the density, but they are. But for the top one, again, you measure the forces and you assume that the velocity is 15 meters per second and the density is 1.2 kilograms per meter cubed. You factor those into the equations. You now have a lift coefficient of 1.1593 instead of 1.131. So that's a 2.5% error between the top and the bottom condition, even though you assume that they're the same conditions. The drag coefficient is 0.0926 instead of 0.091, a 1.5% error. So before we go any further, I want to talk about why these errors occur, because they're different. So the lift coefficient error is 2.5%. The drag coefficient error is 1.5%. Why are they different? The reason is because you not only have the direct error due to the error in the density, you have the indirect error due to the change in flow physics. Because you have a different velocity, the Reynolds number is slightly different, the lift and drag productions are different and they don't change linearly. So the lift will change a certain amount and the drag will change a certain amount. They won't change by the same amount. So you can't factor that in again, which really makes this error a real, I want to say a real bad word here, but it's really bad to swear, so I'm not going to swear. You should wash your mouth out with soap if you do. Anyway, the error is not consistent, which makes it really difficult to work with. You can't even normalize it later. You can't factor it in. It's either you do it when you do your research, or that's it. You can't factor that in when in the post-processing, and your data is going to have that error forever. So the reason why we have this change in flow physics is you can see on these two figures. For those of you listening to this podcast, you can see these figures on our YouTube channel. We have our podcasts on there with the video associated, or I can just describe it to you. So the top condition, which is the condition where the temperature and barometric pressure and humidity are different, so the temperature and humidity are higher, the barometric pressure is lower, which corresponds to a typical condition, a typical relationship. The pressure on the top surface, so the suction surface, is lower than for the other condition, and the pressure underneath is slightly higher than the other condition. And also the low pressure near the leading edge is slightly more engrossing than the other condition. So that means that the flow physics is different. That's why we get the change in this error and drag. And also to go with these two figures, I have this figure here, if I can get to it. Okay, these two figures, this figure here has the two conditions at the velocity now. So it shows you the velocity map over these airfoils. And immediately you can see that the wakes are different. Near the trailing edge of condition 1, which is very close to what we assumed, is 14.98 meters per second instead of 15 meters per second. The wake is significantly greater than the condition 1, where we had a higher velocity. That makes sense because if you have a higher velocity, you have a higher Reynolds number, and that suppresses stall. So we have a smaller stall pattern. Now that's bad news because stall is a very important phenomenon that we want to measure and get right. And if we have errors in the velocity and they're creating these errors in this stall pattern, then we're getting wrong data, which is why the lift coefficient changed more than the drag coefficient. This wing has not undergone deep stall yet, and we're not at that precipice yet. So if we were to push the angle of attack a little bit higher, we'd then get to the point where you'd get that massive drop off, and then that slightly increased velocity for the condition 2 would result in a much greater drag increase. But here we haven't reached that precipice yet, so we've just increasing the lift more than it should be compared to the drag. And also over the top, you can kind of see that the near the leading edge, the velocity is a little bit more engrossing as well in terms of the high, that peak there. So this is what the error in the density does. So how do you get rid of it? Well, we make an instrument that measures the temperature, barometric pressure, and humidity very accurately. It's an aerodynamic instrument. It's made for research purposes. The error is very small, and it will push out the density of the air for you. You can also use these values that it gives you as well. So it gives you the temperature, barometric pressure, and humidity along with the density that it calculates. And you can use all these values for whatever purposes you need. So for the density, you can factor that into your wind tunnel. So when you're in the wind tunnel, you have this instrument, which is very easy to use. You just plug it into the power and you stick it on the wall. You can see it. It has a screen there, so it's very nice. It's called the Hemisphere Hawk. The link is in the description. Anyway, you have it in your wind tunnel, and you then use this value, the density, to calculate what the dynamic pressure should be to get the velocity that you want, and also corresponding to the correct Reynolds number. You can then change the velocity in your wind tunnel to get the right the fan speed to get the right velocity in your wind tunnel based on the dynamic pressure, and also the right Reynolds number. So you can fix it right then and there. If you don't fix it right then and there, as I mentioned earlier, the flow physics will be wrong and you can't fix it later in your post-processing. So it's either you fix it then or forever hold your peace. So that's how you get rid of the error in the density, and this is the major error that most aerodynamicists find. In fact, I remember one incident, for example. This was quite a number of years ago when I was first using the Hemisphere Hawk, and I was doing research, and I found that this particular airfoil that I was using, it had significantly different characteristics to what we'd expect. And I went through all the data and it all checked out. I ran the experiment again, it all checked out. I published the results. And then this other research group, they did the exact same experiments because they saw our experiments and they were like, wow, this is weird. So they want to do it too. And they found different results and they were like, well, this doesn't make sense. They found this, but we found that. And then it turned out that, well, they weren't measuring the density. And then that gave them wrong results. So once they did measure the density, actually another group did it and they measured the density and then they got the exact same results that we got because they held that constant. The other group that got different results, they didn't measure the density, so the errors were in their results. And so that's why they couldn't find the same thing we found. So that led us to producing quite a few papers on that phenomenon that no one else was able to find because we were calculating the density and then factoring that in. So we had that error under control, whereas everyone else didn't have that error under control, and it made that in that particular case, it actually led to a 10% change in the drag coefficient. It was 9.5%, I think, because the flow physics was different, and the lift was about a 2% change in that particular case. So that's why you want to measure the density accurately, and that's one case study that I just threw out there to show you what can happen if you don't. Anyway, so that's the end of this podcast. Make sure to like, subscribe. If you're not measuring the density, make sure to measure it. You can use our Hemisphere Hawk. It's very easy to use, and it makes your research far better, and you don't get these problems, and you can find stuff that no one else can find. It's really nice, and it makes the process of publishing results so much easier because you're finding stuff that other people can't find. So it's like it's not playing. It's just so much easier. And anyway, so make sure to like, subscribe, and see you next podcast. Peace out, amigos.